but still looking for a few more quiz solutions or quiz responses. We have 2 so far. Okay, I'd love to see just one more, and then we'll review. Okay, let's go ahead and dive in. I love that everyone got this one right. Nice. So you multiply one by the other, right? So not a trick question. Okay, cool. So we're just gonna skip that. Okay, so this is a review back to 2 weeks ago now. What activation function works best for prediction of an output with multiple categorical values? So in fact, it's softmax. So sigmoid is great for dichotomous or binary outcomes. Softmax is appropriate when you're doing a multi-class prediction. Okay, and then this one is the one I'm most interested in reading, because we're actually going to review some one-hot encoding tonight as we dive into recurrent neural networks. So the question is, what are the differences between ordinal encoding and one-hot encoding, and when would you use each? And so technically, if you only put either one-hot encoding or you answered about ordinal, you technically wouldn't have gotten it right if this were a real quiz where we actually, graded you. But just in terms of the complete answer, we're looking for a discussion of both. So, most of these actually didn't answer both. I think this one encapsulates the best solution, although it's not 100%, but it's my favorite. So ordinal encoding gives it numeric values, right? So it's not necessarily at random, because you can actually define the ranks. You don't necessarily have to assign them randomly. But basically, it's wherever there is order implied in categorical variables. So like a defined order. So that's a great way to describe it, right? So, it doesn't work for things like mutually exclusive, like male and female, right? well, I guess I'm technically, anyway, wouldn't work for something that doesn't have intrinsic order or rank. If one thing comes after the other, things like day of the week, that's what you want to use ordinal encoding for, right? One hot encoding is good for pretty much anything else, like the male, female, or obviously we don't live in a binary universe. It could be male, female, cis male, cis, female, trans male, trans female. So a one hot encoding example there being each one of those categories can only have one value. So let's say that someone identifies as a female, and just female, nothing else. There would be a one value in that female column, and all the rest would be zeros, right? And so it creates this long vector of ones and zeros for which there is only one value that applies to whatever that category is. So one hot encoding is great for that kind of like mutually exclusive stuff, not great for ordered. Okay, so that's, if there are any questions, go ahead and let me know in the chat. What we're going to talk about tonight involves SageMaker. Go ahead and stop this share and hop over to my SageMaker instance. So you're not going to be able to follow me live coding on Colab. Unfortunately, Colab is an awesome teaching tool, but it breaks. We're starting to get in the universe where we really, really do need these larger servers, which means that you need to start making use of those Amazon credits that Lambda provided for you. If you guys have any problems setting it up, I don't want to get into that tonight because we have a lot to cover. However, I am happy to spend some time during Q&A/office hours tomorrow if you want a little bit more help getting set up on SageMaker, or reach out to your TLs to get that started. Okay, let's go ahead and dive into our notebook for tonight. Sure. Okay, I'm actually really excited about tonight's because we're finally, we spent all that time last week or 2 weeks ago, I guess now, basically reviewing the fundamentals of neural networks. What we're going to be talking about here are getting into the higher level architectures. So we talked last time we got together in the last sprint, we talked about perceptrons, we talked about multi-layer perceptrons. All of those together are known as feed-forward networks. Feed-forward networks include steps like gradient descent and backpropagation, which we're not going to go into great detail. The good news is you guys will probably never have to go through that ordeal where we wrote the comments out and wrote everything again by hand. Everything moving forward is going to be very, very abstract. And that's important because in the next 2 weeks, we're going to be reviewing a lot of different things, which unfortunately that means we're not going to be able to get into a lot of depth on these topics. And so I want to encourage you guys to think of this as an overview. So I want you to have an understanding of how to apply these architectures and to what types of problems they're the most applicable. That way on the job, when you come across in particular like a time series problem that we'll talk, something we'll talk about today, you'll know, oh, recurrent neural network, that's something that might be a possible solution to this problem. That doesn't necessarily mean that you're going to be an expert and are going to be able to encode it, from muscle memory. But what you can do is you can go back to your notes, your commented code from these lectures, and you'll be able to remind yourself of some of those details. So that said, we're also not going to be able to get into the nitty-gritty of how everything works. We just don't have time for it. We're going for breadth in this sprint, not necessarily depth, whereas we had done that, whereas we sort of went for an in-depth understanding of how neural networks work with backpropagation and gradient descent. So I both apologize, but more importantly, just need to put that out there because there's a level of just accepting what we're talking about. And if you want to do more reading on your own time, that's great, but you don't need to have a deep understanding of these architectures to do well on the sprint challenge. or really even to succeed as a data scientist. Okay, so now that that long disclaimer is out of the way, now we get to the fun stuff. So one of the most in-demand skills I'm seeing in job descriptions and even in the types of projects that I'm doing day to day as a data scientist are time series, right? When I first started at Lambda, I actually said, oh, we have to have a whole section on time series. And there are different types of time series. There's a traditional what's called traditional time series, where there's a lot of, I can talk more about it during office hours tomorrow if you want, but bears a lot of similarity to the way recurrent neural networks work. But I just want to highlight that it's very important because time series is basically predicting the future, right? And who wouldn't want to do that? Who wouldn't want to try to predict stock prices or, if it's going to rain tomorrow? It's understandably important. Okay, so at the heart of it, recurrent neural networks are appropriate for what's known as sequential data. So there's only 8 of us in the course tonight, or in our in the cohort. So just unmute yourselves. What comes to mind when you think of sequential data? There's time series. What other types of data or problems might have sequential data?
Data with unique
Treasury
IDs.
bills.
I heard treasury bills, and what was the other one? I think Tyler, you said?
Yeah, I said data with unique IDs.
How is that sequential?
Well, like if you have user 1, user 2, user 3, or that's my thought.
That is, yes. Okay, so yes, you did answer my question. That is indeed sequential because order matters, right? And who said treasury bills? Why would that be sequential?
Just in terms of keeping track of them, so that they are to prevent fraud. They usually put out certain numbers. Well, they used to be back when bills, they were put out, and you got to take the bill home. That bill would be once you cashed it in, there'd be a number that would have to be reported by the bank.
Yes, absolutely.
The Treasury.
So you guys are both sort of talking about the universe of unique identifiers, right? And so as something increases, order matters, where there's a difference between 1, 2, 3, 4. You're talking about the number of prints that a painter comes out with, right? Or any other artist. 1, 2, 3, 4, there's a difference, right? In terms of prediction, what are some different types of values we may want to predict? Not just stock prices, although I'm sure everyone wants to. What are some other things that come to mind? Like what types of problems do you think we might be able to apply?
Like housing predictions, housing costs?
Absolutely, because it's generally increasing over time.
Better
Anyone else?
weather accuracy?
Yep, better weather accuracy. Although they've gotten pretty good in the last couple of years, I'll admit. One that came to mind for me was actually DNA. DNA is near and dear to my heart. For those of you guys who were in office hours before Thanksgiving, you heard me go on a rant about why it's such a flawed science. But essentially, DNA is a sequence, right? And you read the way it works is you read different, you don't, but the molecules that make life happen read the sequence in a particular order. So order matters, right? There's one more thing that you guys spent a lot of time on. It was right before you met me. What did you guys work on in the first sprint of this unit?
NLP?
Text. Yeah, exactly. Text and natural language, where order matters, right? If I type out the letters A, B, C, D, you guys know what comes next. Or native English speakers will generally think E, F, G, right? Or if I have a sentence like C spot, like what happens after that, right? Like C spot run, right? Or C spot jump, or C spot do some action, right? So there's an order that matters that conveys meaning. And so just at the bottom of, at the very base of this, at the heart of this, a sequence is an enumerated collection where order matters, right? And repetition is a layer that you can put on top of it. So oftentimes you're going to see things like a really sophisticated repetition would be seasonality, right? And so when you're predicting things like stock price, you may see things like there's an increase. I don't know, I'm just making this up. I'm not an economist, but let's say there's a bump right in December, right? Because it's during the spending season, right? And companies are generally doing well if Americans are out on Black Friday spending money. Anyway, so repetition is also something that is also a dimension to consider when you're dealing with ordered values. Okay, so time series shows up a lot. And actually, I will say pandas in particular, what handles timestamps really, really well. We're not going to dive into time series tonight. I'm again happy to talk about it tomorrow if you want to know a little bit more about some of the projects I've worked on. But just know that the stack you guys are learning is it equips you very well for dealing with timestamp data. Okay, so let's dive in. What does that have to do with neural networks? Well, recurrent neural networks are a class of neural networks that work very, very well for sequential data in particular, right? And so the way this works, and I'm not going to dive into, again, not going to dive into a lot of detail on this. I'm going to try to keep it very high level so that you can have a conversation about it during an interview, but not necessarily make you an expert in neural networks. A recurrent neural network implies the presence of recursion, right? And so remember in that node diagram, we had, if we were to draw, we have like our input layers, right? And we basically had just make it very simple. And we had one hidden layer and then one output value, right? All of these are just going forward. That was the definition of a feed forward network, right? In a recurrent neural network, we actually have the ability to feed back on itself, right? And so at a very abstract level, I want you guys to think about a recurrent neural network as a neural network that is basically iterating a loop through the nodes, right? And so looking at this diagram a little bit more closely, the recursion or the recurrent piece of it is indicated by this circular edge, right? That comes back and feeds back on itself. This is what's known as the folded schematic, the folded diagram. If you unfold it and have a little bit more detail to it, you can actually see some of the elements of recursion, right? Where we have a hidden layer, we've got an input that includes the prior value. You've got your t-1 value here. You've got an input that corresponds to x of t, and then you've got some value that represents the next layer in the recursion, right? And so you can, there's all kinds of different architectures that build upon this, where you can take, so you have the inputs, you've got your hidden layers, and then you've got some outputs. Generally, the outputs are used to kind of like feed into the outputs of the hidden layers are used to feed into the next layer, but that's not necessarily always the case. You can make predictions on these three different values. I mean, there's an exponential number of different ways you can organize these architectures. So all of that to say, the concept here is still very, very similar to the feed-forward networks we've talked about before, where there's an updating of the weights. You're going to basically move forward and make predictions, go back and adjust things. Back propagation still plays a role, and you can still train these in a very, very similar fashion. I mean, I think our final model tonight is only going to be like 3 lines, like when you finally get to the Keras part of it, and so it's very abstract, but also very, very straightforward. However, if we were to think about this as a sort of strictly feed-forward network, The problem with recurrent neural networks as a class is that because we've got this recursion piece and we're kind of iterating through it, it's different than a feed-forward network that kind of has a fixed length, right? Or a fixed set of dimensions to it. And instead, you've got this feedback which allows you to, which can have exponential consequences. And so, as you can imagine, if we're increasing the weights by a large number each time, the magnitude of those weights gets exponentially bigger. This is something called the exploding gradient problem, okay? And I'm not trying to define that in a way that's going to make you an expert. I just need you guys to know that that is an issue with sort of traditional recurrent neural networks. Conversely, there's something that you actually hear a bit more about called the vanishing gradient problem, which is just the opposite, right? Where you have, if you have some sort of weight update, but it gets smaller and smaller and smaller and smaller, that's where, it can kill your network because it'll fail to converge because you just have these infinitely small numbers. So to get around that, there have been some updates to sort of like the more traditional vanilla recurrent neural networks. And the one we're going to talk about tonight is something called the long short-term memory unit, or an LSTM network. Let me go ahead and turn off my annotation and scroll down. And we'll dive into what this diagram means in a second. But what we're able to do, so there are two things that are issues with the standard neural networks: vanishing gradient and the exploding gradient problem. But also, the research bore out that just these traditional recurrent neural networks, the vanilla implementation, actually they were biased towards the later values, right? And so let's say that you had 20 values in your sequence, right? And you make a prediction on the 21st value. The values for 18, 19, and 20 would have more weight, more impact on that prediction of the 21st value than the prior ones. And so by updating it and using this concept of a long short-term memory unit, it basically gives the older values are not forgotten, right? They don't fall off the waist. They don't fall by the wayside quite as much, right? And you have a little bit more control over how much or how little the recent or the more distant values, the initial values, have on your next prediction. Okay, so that's a lot of talking. So I'm just going to pause for a second and check Slack to see if there are any questions. Let's see. Oh, okay. So I actually saw some questions about the quiz. Let's touch base on that later, because I'm genuinely not sure what was going on there. I'm sorry if some of you guys got it wrong, but for some reason, yeah, my bad. Not quite sure what's going on with the quiz. Okay, so I don't see any questions related to the stuff I've talked about so far. So let's go ahead and plow ahead. Okay, so what is LSTM? Why do we care? Effectively, what LSTM does is it has this concept of gating, right? And so as part of that recursion element, it allows there's an explicit step that will allow certain values to be amplified, sort of as an explicit step. So in other words, that's where the sort of like amplifying the short-term memory comes into play, or forgotten, right? Where certain signals may be diminished. Obviously, This is where, or maybe not so obviously, but this is where different activation functions can definitely come into play. I don't want to get into all the nuances of this. Suffice it to say, from this, what I want you guys to know, I want you to understand what the vanishing gradient problem is, the exploding gradient problem is, and if you want to read a bit more about it, I highly recommend this blog post, the unreasonable effectiveness of recurrent neural networks. And of course, there are a lot of other materials out there if you're looking for more than just the superficial survey level overview that we're going to have today. Encourage you to go read some deeper dives in blog articles and that sort of thing. Okay, so what we're going to do tonight is we're going to spend some time doing two things. You guys have a lot of experience, or a whole sprint's worth of experience, dealing with text data. And so that's actually what we're going to deal with tonight. My favorite part is we're going to produce a really bad model that basically predicts some text based on the news. And your assignment tomorrow is going to be to predict text better than mine did, which is not going to be hard, I promise, because it's a really bad model. But it's still really cool, because what we're going to be able to do is see what the model is actually pulling out and print out that text. What I would say is that recurrent neural networks are fabulous for, in theory, any sequential data. But I think that in practice, recurrent neural networks have sort of like found their, have been in the spotlight for specifically in NLP and sentiment analysis, in, basically in text-based applications. So we're going to kind of stick with that as a proof of concept. You can do a lot more with it, but the fact is, predicting the future is just really hard in a lot of cases. And in particular, recurrent neural networks can be, I'll just put it this way, they're kind of annoying because there are a lot of like really weird little tips and tricks that you kind of have to remember to get them to play nicely. And it varies by data type or problem type. So for instance, they're not, to the best of my knowledge, they're not really widely used in DNA, in genomics in particular. They can be, but they kind of had limited applications. So in theory, they can work on any sort of sequential based data. But again, for sake of our conversation, we're just going to stick to text based. Okay. So we will, so let's go ahead and dive into our notebook tonight. And I'm just going to run this as we go down, because some of this is going to take a little bit to run. So we're basically going to be pulling a couple of new things. We're going to be dealing with Keras again. We've talked about the sequential model in past lectures. What we're going to be doing is actually pulling out a new type of layer, the embedding layer, and an LSTM layer. And this first initial example is going to focus on a Keras toy dataset, the IMDb dataset. And what we're going to do is we're going to pull out the values of this toy dataset. And effectively, let's go ahead and look at this. So because this is a toy data set, this is actually already cleaned for us. So we're going to spend a lot of time in the next example where we predict text doing the encoding of the data. But for our purposes right now, this is just a demo. So we're pulling out the IMDb values. We're only going to include 20,000 features. We're going to have a max length of our sequence be 80. These are somewhat arbitrary numbers, but it allows me to run this without blowing up my extra large SageMaker instance. And we're going to call a batch size of 32. And because this is a toy data set, we're actually just going to call the IMDb object with the load data with the load data method, where the number of words is just going to equal the maximum number of features we want to deal with. And so when we pull out the train sequence, the training values and the test values, we've basically got a balanced set. We've got 25,000 values in the train and 225,000 in the test. Okay, but let's go ahead and take a look at what's going on in here. So if we were to print out, where'd it go? Okay, so if we're gonna print out these, print out the first value in our training set, this, like I said, this has already been encoded for us. So we shouldn't expect these numbers to have any particular meaning, because they don't when we're passing it in. The encoding and decoding part is actually one of the most time intensive pieces of training one of these networks. I mean, you guys, I don't have to tell you guys spent all that time dealing with it during the NLP sprint. But just a reminder to give yourself plenty of time and have plenty of patience with yourself when you're dealing with data cleaning, because text is inherently obnoxious. It's just a difficult thing to deal with. So the goal of this example is just to walk through what kind of the basic syntax of an LSTM network might look like. And so what we're going to do is we're instantiating a new sequential model. We're going to add a new embedding layer with the max number of features, and it's going to have 128 neurons. We're going to add an LSTM layer as our middle layer, and then we have a dense layer as our final. We have an our activation function is sigmoid. You guys are familiar with all the rest of this. We're going to compile it. We're going to use the binary cross entropy as our cost function. Our optimizer is Atom. We're going to print out the accuracy metrics. We're going to fit it. We're going to use 15 epochs. Hopefully this is not going to take forever. Let me go ahead and actually, I'm not going to run this because some of these do make it explode. And so, going through, let's go ahead and run this. Let's see what it gives us. Gonna run? Not running. Okay, 1 second. It doesn't. Why is it not running? Oh, no kernel. Love that. I love it when it just randomly starts that. Okay, let's try that again. Okay, so while these are running, I'm actually just going to pause and see if there are any questions so far. So we want to run all above, and we'll go ahead and let that go. 1 second. Okay. Okay, no questions so far. Awesome. Let's just go ahead and give this a second to run. Okay, this is what I'm afraid of. Oh, someone have a question? Go ahead, speak up.
Yeah, so when you're saying text has some inherent sequence to it, how does that actually work? Because, any word can follow any word, and any sentence can follow any sentence. So what kind of series or sequence are we talking about in text?
I guess I mean the semantic value, so the literal meaning of it. So if you have a sentence and I say, Keri asked a question, is inherently different than a question asked Keri, right? Where the second one doesn't really make any sense, right? And so that's where order matters, where you have the noun followed by a verb followed by the, I guess it would be the object of the sentence. Does that make sense?
Yeah, makes sense. But
Yeah.
I think it'll trip up when it's, I don't know, looking at Shakespeare or something, because that'll be like weird.
Because it feels like it could be random, right? It's hard. So just because, and that's actually a good point. One thing that's implied with all of this is that we're able to understand the order, right? And that's in part why, recurrent neural networks are great for something like text, because we can read something and tell pretty quickly if it's right? And so it's easy to then feed back onto our network and tweak things and adjust those hyperparameters or change something about the input, right? So it's easy to iterate on that because we're all experts we're all literate, right? So we can all read and we can all apply meaning. For something that we know less about, something like DNA, we're not going to know if, spitting out a G or a T is actually harmful because we actually don't know much about that data. We don't know enough about that sequence to understand how we should adjust our model. So yeah, but that's actually a really great question. Well, while we're waiting for this to run, and actually I think I'm gonna stop this, which is what I did before. But all of that to say, the whole point here was that this is, in a nutshell, this is how we train our model. We're going to print out some accuracy. It's exactly the same as we have dealt with Keras models in the past. We are going to dive into each step in a little bit more detail in the next learning objective, but I wanted to give you guys like kind of end-to-end, what's that code? What's the minimum number of code that you would want to have in your cookbook, in your data science cookbook, your list of recipes for applying one of these or for building one of these before we dive into the nitty-gritty of it. Okay, so yeah, you can see why this is an extra large server and it's still taking forever. So yeah, okay, I'm just gonna stop this. I'll start it again during the break or something when I don't need, but I need to run other stuff. Okay, so what I want to do is I want to take a deeper dive into what's going on. And I actually want to build something with a little bit more transparency. I mean, it's great that it's making these predictions and it's spitting out this accuracy, but what does that mean? So in the next part here, we're actually going to build from the bottom up. We're going to analyze a sequence, and then we're going to actually use it to generate some text. And so we're basically just going to be pulling data from newspaper articles. In your let me go ahead and see if I can pause this and create. I'm going to show you what these this looks like. So if we, in the GitHub, it's actually going to be a child folder called articles. I was kind of tired of battling with pandas about reading the files, so I just put them all in the same directory. But effectively, what we've got here are chunks of text data, right? And so each of these is an article. It's not interesting necessarily, but it's language that you would use, and we'll see if we can make some predictions based on this. So we've got a bunch of different stuff in here. We've got things like numbers. We've also got, obviously, we've got alphabet characters. We've also got some white space characters, right? And so we've got the new line. We've also got some like spaces in here. Hopefully we don't have anything too exotic. But just to say that not everything here is necessarily going to have meaning, right? It's not necessarily going to have the same meaning. And so while there's meaning to us, that doesn't necessarily mean that the neural network's going to pick up on that. Okay, so let's go ahead and hop back. And so there are, how many of these are there? There are 100 and some odd. I want to say 130 something of these chunks. 135, it looks like. Let's see. Oh, this one looks like it's blank. Oh, no, there it is. Okay. Well, that's interesting. This just looks like gibberish, actually. Does it? Mixed animated shorts. Oh, no, this is about someone in particular. Okay. Anyway, so different information. These are basically just articles. Okay. So what we're going to do, and so I'm actually going to adjust this a little bit. So we're going to be doing some, so in the GitHub, if you uploaded those into a separate subdirectory, you would use this connotation because for some reason Pandas hates me. I'm actually going to adjust that. What we're going to do is call os.current directory. So os.current, I believe. Oh, no, we need to run our imports first. Okay. So let's go ahead and see what kind of data that included. So what this does is it pulls, OS is a library or a module that allows you to work with files on your local operating system. In this case, it's local to SageMaker in that particular instance. So anything that I uploaded, I'll be able to interact with. And so what this does, let's go ahead and print that. This creates a list of all the files in my current directory. Now, understandably, this poses a bit of a problem, right? Because we've got, we don't just have text files in here. We've also got our IPython notebooks. We've got the lecture notebook that we're running from, right? And so we're gonna have to do just a little bit of cleanup to parse this out. So before we get to that, we need to pull the data in by hand, and then we also need to get it into a format that can be digested by the neural network. Okay, so I'm going to create an empty string. We're just going to call it text. And what we're going to do is we're going to import everything. We're going to cycle through each of those files, pull the data in, and basically just add it to the end of this text string, because that just makes it a little bit easier for the neural network to ingest it. So let's go ahead and we're going to walk through every single file in that data set. However, because we have multiple data types in there, we're basically going to say if the last 3 values in the file name equals text, txt file, then we want to do something with it, right? And so we're going to call the path, we're going to call it file name. And then you guys might not have seen this before. I don't actually know if you went through this, but there are different ways to pull data into Python. The way to use native Python built-in functions involves a with statement. And what you're going to do is you're going to close my string there first. You're going to basically open this file. You're going to read it, and you're going to kind of iterate over it. And so what we're going to do is we're going to say our content is basically going to be the data that we're reading from it. We're going to read the content of the data object and basically stuff it into the content object. And then we're going to say, okay, we're going to update our text string and say we want text to equal the prior value of text plus space. And then we want to add whatever that new content is. So let's go ahead and make sure that this works. Cool. And that actually worked a lot more quickly than I was expecting. Okay, so we've got a corpus length of almost 900,000, right? Let's see, what does that actually mean? Like what's inside this text? So let's say we just want the first 50 Okay. So basically, we've got all of this, we've got all of our articles put together, right? We've got a lot of data here, a lot of data, which is why we want to be really careful about what we're printing out. I will actually say, guys, if your models are taking a long time to run, consider how many steps you're printing stuff out, because printing stuff out is actually very computationally intensive. And so notice how it was just printing out the first 50 values of this, I guess it's an array, or this list, sorry, but it had to pause for a second because there's a lot of information here. So when you're printing stuff out, just be sure to be very careful about what you're printing out. Okay, so if we just look at the first value, you know, and I'm sorry, scrolling through this also makes it a little bit hairy. Need to be careful. So we're just printing out the first value here, right? But that includes a ton of data, right? Let's go ahead and take a little bit, let's see, what if we were just to print out, okay, so let's just, instead of looking at the first, like, let's go ahead and take a look at the last 50 characters, instead of like the first one, you know, through the end. We've got a couple of pieces of information here. So we've got the /n, we've got a couple of like white space characters here, presumably they're spaces, and then we've got some other meaning, then we've got some other characters, right? Keri McLaurin makes a touchdown catch and the, you know, something. Okay, so in order to feed this into our neural network, we need to encode the data. We also need a way to decode the data, right? And so there's actually, and we're going to do this one character at a time. So the difference between what we're doing tonight versus what you guys did in your NLP exercises is that we're going to try to predict specific characters, the next character that might come in a sequence. We're not necessarily going to predict the next word. That's for you guys to do tomorrow night as part of your assignment. But as a proof of concept tonight, we're basically just going to walk through predicting a single character that comes at the end of a sequence. And we'll go take our break in a minute, but what I want to do is actually get list, and we're going to go ahead and build our encoder and decoder. Okay, so what I'm doing here is I'm basically taking a list of the unique values of characters, and we're going to sort it. Now, why, if I want unique characters, what is it about, what about my code here is giving me the unique values? Go ahead and unmute yourselves and speak up.
Is it that we're sorting it?
Well, sorting would put it in order, right? But that's not necessarily just going to reduce it to the unique values, right?
It's set that target.
It's the set notation. Yep, it's the set. And so what set does is it's actually just going to pull out the unique values. And this is a trick I use all the time. If you're trying to pull out the unique values of a list, which you'd be surprised how often it comes up, use the set notation, or the set concept, function, I should say, or the set object, because it's very, very, very fast. Don't try to create a loop. Don't try to use the .unique attribute or method. Use set notation. Comes up a lot. Okay, so effectively, let's go ahead and take a closer look at what this is. This gives us a sorted list of the unique values in our text. And all I did was pass in all of the text. And how quickly did that run? It ran really, really fast. So what are those unique values? What are those unique characters that we're going to be trying to predict? We've got the /n. That's what's called a bridge return or new line value. We've got a white space, we've got a space, we've got, and a couple of other things. And how many, it looks like we've also got some emojis in there. I wouldn't say that's necessarily very professional, but it's, just good to know that we've got our stars, we've got our fractions, we've got some ellipses, which I didn't even realize was a character on its own, but we've got some interesting values here. So if we were to be doing something more sophisticated with this, it might be worth like stripping these values out and only pulling out the alphanumeric values or white space characters. If you guys find you want to do that, regular expressions are very, very helpful. Do it all the time. But for now, we're just going to acknowledge the fact that we've got that we've got some ghosts and thinking emojis in there. Okay, let's go ahead and what we want to do is we want to create a dictionary that's going to convert our characters into an index value. So basically, we want to encode it as a number, 1 through, let's see how many values are in 1 through 121. And the way we're going to do that is to say, let's call it our indices. And it's going to be a dictionary. And what we're going to do is we're going to enumerate through the values in that cars and that characters cars list. And conversely, what we want to be able to do is translate the indices to characters. And we're going to do basically the same thing, but we're just going to reverse the values of the index. The index value itself, like the 1, 2, 3, 4, is going to be the key, and then it's going to return as the other part of that dictionary the special character or just character. Okay, I know that's a lot, but this is an important, oops, should probably run it first. So what's inside that? So basically in our encoding dictionary, we've got the character and we've got an index value. So if we see a new line, the index value on that's going to be 0. Okay, so we're at 8 o'clock. I've been doing a lot of talking. I want you guys to get away from your computers for 5 minutes. Leave your questions in the Slack room or in the Slack chat, and we'll review when we get back. And you guys know the drill. Get up, move around, get away from your computers. I love your beautiful faces. I don't want to see them for 5 minutes. We'll see you guys in a few. Okay, and there's our timer. And I'm going to go ahead and pause because I want to see if there's any questions in the chat. Okay. Okay.
Hey, Keri, by the way.
Yep.
The thing a lot of people noticed during the quiz is that the last question had 2 text boxes to enter your answers. And so people like me, we thought you enter the first answer on the first box and the second one on the second one. So I don't know. There's probably just a mistake in.
Nope, nope. I know exactly what happened. Oh. That's my bad. I'll address that when we get back. Thank you for flagging. I appreciate it. Okay, get up, get away from your computer, Martin. Okay, see you in a few. Okay, welcome back, guys. Give everyone another minute. I should say hi, Annika. You're the only one here, so.
Could you do me a favor and scroll up in your notebook a little bit so I can get a
Yeah.
couple code cells I missed?
Totally. Yep, totally. And someone actually asked, how do we follow along? So that's going to be my next thing. Okay.
Great. This is perfect.
Totally. And I will share the notebook itself when I'm done with class, when I'm done typing this out. Because, you know, honestly, I really, really don't want you guys to focus on like typing it out while I'm talking about it, because it's really hard to focus on what I'm saying versus what I'm writing, right? However, I hate to do all demo, like walking through pre-existing code, because it's a really flat delivery and it just makes people fall asleep. So I like to mix it up by doing kind of like a live coding versus, you know, explaining the code balance. To those of you guys who are back, don't worry about trying to get every single step, right? If you want to take notes, write comments to yourself in your code in the notebook, and sort of like explaining what you expect each thing to do. And then I would recommend you go back after I release it at the end of class. That way you guys have the key and you can actually just layer it back in. It's up to you. You're welcome to write it down or type it out as I'm speaking. It really depends on how you most effectively learn. I'm an audio learner, and so I listen, or I learn by listening. And so for me, that was the most effective way for me to ingest material when I was listening to a lecture about a highly technical topic. Okay, welcome back, guys. So there were a couple of questions, Ashwin specifically. So Ashwin's question, what do the embedding and LSTM layers do? Great question. We're actually going to get to that in a little bit. So I'm just going to put a pin in that question, because I will, when we take the data we're cleaning right now and plug it into a model, I'll explain it there. And then let's see, another question was, and then Ashwin's question was, do we follow along in the next stop? So does that question mean, I think the question was related to what I was just saying, where do you need to, so yeah, I'm going to be doing some
next
oh,
step.
sorry.
No, I meant next step.
The next parts of our, yeah, so basically these next three, yes, I'm going to do just a little bit more of live coding, and then we'll go through this. So it's live coding. It's not, I haven't given you that code yet. Okay, cool. And Martin, thanks for the context. Just to sort of like, let me acknowledge the quiz thing, the question was, the 2 text boxes were my mistake. I deleted that last question because it was just it was a separate question. It was a different text box. And so I think in doing that, I erased your answers. So I apologize, guys, for poor design on the quiz today. Now I understand that people did answer the question, but it was separate. So sorry for giving you guys a tone of voice that was not appropriate. Saying you didn't answer the questions. You did answer the questions, and I'm glad that makes me happy. So thank you. And I won't make that mistake again. I won't throw your answers away, I promise. Okay. So for those of you guys who are just getting back, there was one question that Ashwin asked in terms of what does embedding in the LSTM layers do. I'm going to explain that when we get to the model building part itself. But before we do that, we actually do have a little bit more data cleaning to do. But before we dive in, do you have any other questions, or what questions do you have? It's a good stopping point because I'm going to be talking for the next 20 minutes.
I have a question. So we just split the whole sentence into each character.
Mhm.
So what are we trying to do here? Are we trying to kind of predict the next character? And
Yep.
okay.
Yep. Nope. That's a great question. That's actually what we're going to do right now. Is break it up in a way that is meaningful, and then we're going to try to predict the next character.
Okay. I mean, like, okay, sure. Because this will not work because it's just 50 characters, right? So how is it going to learn how to predict the next character?
It's 121 characters.
Okay. I mean,
Yeah.
but still, 121 is. I'm just asking because we don't expect a good read from this, right? Good prediction.
Well, not necessarily. It depends on how much you're feeding in. So we're actually going to feed in 40 characters, right? And that's kind of the fun of, that's what we're trying to do here. Is we're just trying to build, and you're right, because I think I gave it away at the beginning. It's going to be a pretty bad model. But my goal is to give you guys just kind of the basic infrastructure that you need so that tomorrow, when you're dealing with a Shakespearean sonnet assignment, you're actually going to improve on it pretty easily. But candidly, it does take a lot of memory, right? And I'm actually operating on my own personal SageMaker instance right now because my AWS hasn't been approved yet, because I didn't know I was supposed to do that till last week. And so it's a poor model because I don't want it to run for 20 hours. But as a proof of concept, this will actually work pretty well. So to answer your question a little bit better, let's go ahead and dive into the next steps of our model. So basically all we've done is we've just created an encoding scheme, right? And so this allows us to reference our characters by an index and the index to the characters, right? So we can go from one direction to the other. Okay, and so what we're going to do is we're basically going to divide our data into 40 character increments, right? What we're going to do is we're going to, when we're binning it, we're going to move that window over 3 units, right? So we've got a maximum length of our sequence of 40 characters, and then each time we're going to basically just move over 3. So it'll be, I'm not even going to try to draw that. If that doesn't make sense, we'll illustrate it a bit more in a second. Okay, we're going to initialize some empty vectors. Okay, and what we're going to do is we're basically going to be making predictions. We're going to have our sentences or a sequence of values, right? That's effectively our X. And then we're going to make predictions, and we're going to try to predict the next character. So that's effectively our Y value. Okay, so binning this by sequences of 40 characters each, we're going to then try to predict the 41st character and so on. So how do we have this like long, very, very long sequence of text. How are we going to divide this up? Well, it's actually pretty straightforward. What we're going to do is just create a loop. What we're doing is we're going to iterate through each character, starting with character index 0 value. We're going to take the text, the length of the text itself, minus the maximum length. And then we're going to step through it by increments of 3. And these are, honestly, guys, these are hyperparameters that you guys could, not effectively hyperparameters, but these are things you could tweak if you wanted to try to improve this model. Maybe 3 is not the most optimum step. Obviously, it's going to take longer if we're only moving over by increments of 3, because it means we have more chunks, right? If we move over by increments of like 40, then we're going to have fewer of those chunks that we're actually moving through. Okay, so what we're going to do is we're going to append, as we go through, we're going to create an array. And what we're basically going to do is just pull the values into, we're going to grow a list that contains our sequences. And then we're basically going to say, let's take, okay, so let's break this down. We're basically indexing into our really long string here. I is the starting point, right? And the ending point is going to be that index value plus the maximum length, or 40, of our of the sequence that we're pulling out. And then the next character that we're pulling out is going to be just that single next character. Okay? I'll give you guys a second to read this. Okay. Probably been a long time since you've done any appending to lists. So what we're doing here is we're invoking a list here. Append basically adds something to that list, adds an element to the list. And so we're adding the sequence here, and the next character that we're going to train on or test from is going to be in the next character list. Okay. So let's go ahead and take a look at what do our sentences look like? Let's go ahead and, okay, so we've got effectively almost 300,000 of these chunks. Let's go ahead and look at the sentences in a little more detail. Let's see. Let's say we want just the first one. So our first one is basically just a 40 character chunk of text. If we were to type out sentences, if we were to look at the second chunk, it would be sentences 1. And so it's effectively the same thing, right? Notice there's a lot of overlap. That's by design. Because what we're doing is we've got 1, 2, 3 values that differ between the first one and the second one, right? So remember, we basically have this window of 40 units that we're moving over 3 characters each time, okay? So, and here's a question to you guys. Why would that overlap be valuable to train our model on?
It can basically confirm if the prediction was correct or not. I guess that would involve some sort of memory, which isn't what we're invoking here. So
well,
that
would. Well, it's called a long short-term memory unit. So it is what we are doing. So there is memory, actually, right? Like we want it to remember the sequence, and I think you're on the right track. I think just maybe explaining it a different way.
Creating some redundancies, like to make, I don't know, it learn faster. I don't know, it makes sense.
Well, remember, we're predicting one character at a time, right? So we're not trying to predict whole words. And so if we're trying to predict from this, so we have our first 40 characters. We've got white space. Terry McLaurin makes a touchdown catch, right? We know that that next value is going to be C, right? Just by looking at this. Now, think of these as each of these is a different observation to train on, right? And so we're trying to predict the, in this case, the C, that next single character. So step away from the fact that we're trying to predict words, right? We're not trying to predict the whole word. We're only trying to predict that next that next character, right? And so each of these actually become, even though it's redundant to us, it actually becomes a unique training case for that next thing, right? For that next observation. Okay, well, let's go ahead and walk through. I think what's more important is walking through the next step, which is actually one-hot encoding. This is actually kind of one of the key things that you need to take away from tonight. As you guys know from your NLP series, this is kind of useless to any kind of learning. Machines don't handle natural language very well. They really don't even handle like strings very well, let's be honest. Like it's just called an object data type, right? It's not even something that it knows how to digest. So what we need to do is we need to encode this in a way that can be ingested into the model, right? And what we're actually going to do is we're going to create some vectors. We're basically going to be using one-hot encoding to encode the values of each character, okay? And this takes a little bit. So what we're going to do is we're actually going to initialize our training data. I'm just going to copy and paste this with a bunch of zeros to start. Let's just take a look at that. So basically what I've created here is a series of arrays that are equal to the length of our the number of sentences we've got or sequences, and basically just populated it with all false. So it's all zeros, right? So that's just for time purposes. That's just, if you initialize your variables like that and populate it, it's quicker to update subsequently. Okay, so what we're going to do is we're going to walk through sentences. Okay, so what we're going to do is in this step, we're going to, let's go ahead and print. I want to make sure this makes sense to you guys. So in the first part of this loop, so what did I do? Enumerate. Actually, I don't want to print that out. Okay, so we're basically going to iterate through we have a list of sequences, right? That's what our sentences is. That's what our sentences object is. Within each of our sequences, we're going to iterate through and we're going to pull out each individual character. Okay, so for T. Okay, so now we're parsing through each individual sentence to pull out the characters. And what we're going to do here, let me type this out and then explain it. And then, okay, so remember what I did here was I populated multidimensional array or list, that's an array, a multidimensional array filled with false values, right? What we're doing is we're saying for a given sentence, for whatever number sentence that is, for a given character, right? I want you to plug in the encoded value and make it equal to 1 or true. Okay, let's run that and see what that looks like real quick, because this is important. Let's see. We want x0. Okay. No, what? Numerate. Oh, enumerate. Okay, let's walk through that. Okay, hopefully this isn't going to take that long to run. Okay, so remember what we had before was we had a nested array of zeros. What we've got here are some true values sprinkled within, okay? So I would need to hear this from you guys to make sure that you understand this. If we have a true value here and a false value here, let's say we want to go, let's go a little bit farther into this. Let's say we have x because it's nested and it's not always obvious. If we go into the first array, the first dimension, and we take that first value, we go into the next. So we basically take the very first complete array in here. We have false, true, false, 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 false. What I'm doing is I'm one-hot encoding here, right? And what this represents, there are 121 values in this array. So what do you think that true represents?
So that's the equivalent of a 1. So this is array 0, 1, 0, 0, 0, 0, 0.
Yep.
And that's how we encoded this specific character using the one-hot encoding.
Yes, exactly. So if we go back up to the top and we look at our, and we sort of scroll up and we print out our different, let's see, where did I print out the character indices right here, right? So 0 is a line break, right? And the 1, or the second, when we're 0 indexing, index value 1 corresponds to white space. 2 would be the exclamation mark, and so on. And so if we, so we would expect this to be what? If this is true, what is it?
Probably white space, since that was the first,
Yeah.
the second.
Yeah, I think I'm not going to spend a whole lot of time on this, but let's see. Sentences, I think we should be able to do this. Yep. And so basically, remember, sentences is the object which includes the raw string value, right? And if we index in on our X list, or X array, this gives us the encoded values. Okay, now to your question, Ashwin, I know that was a long time coming. What is an embedding layer? An embedding layer is actually what translates this array into an input. So it's always going to be the first layer of an LSTM model in Keras. And what it does is it takes this these arrays of data, it kind of condenses it down in a way that it doesn't take up quite as much memory, and more effectively translates it into a dense layer. So for our purposes, an embedding layer is our input layer for an LSTM network. And what it does is it basically transforms that into an appropriate input layer when you've got these like wide, sparse arrays. Or I should say, in this case, it's a matrix of data. Okay, so if we have a list of indexes, false, true, blah, 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 and we step back, the next layer up represents our sequences, and the layer after that represents our entire corpus, right? So we can kind of drill in, and instead of representing these as characters, we're representing these as true false values, which as you guys know, for a computer, it's way easier to digest. Okay, so that said, let's go ahead and dive into the actual model building. Okay. Well, actually, before we do that, let's do X shape. So we effectively have we have almost 300,000 sequences. The length of each sequence is 40, and there are 121 characters represented in each, in that final array layer. Okay. And I have to do one more thing. I need to, basically, what we did here was we did the one-hot encoding on the sequences themselves, but we also need to do it for the Y value. We're not going to predict anything unless we have some Y values. So let's go ahead and want to do indices next. Okay. And so again, what we're doing is our Y right here, we're establishing an array that's filled with false values, filled with zeros, or in this case. And what we're doing is we're overwriting it with a true value, or in this case, a 1, but because it's a Boolean data type, it's converted into a true value. Anywhere we have, so we're indexing in, so hopefully this makes a little bit more sense. We're indexing in where we have I is a sentence number, and then this is basically just the character that we're gonna put there, that we're gonna predict against. Okay, so that's the 41st character, so to speak. So our X values include the 40 characters. We're gonna try to predict that 41st character. Okay, let's go ahead and build our model. If you guys have questions, now's the time to speak up. Does the concept of this multidimensional array make sense? I'm going to stop talking about it if not, because I do not want to put you guys to sleep. Let's get to the model, right?
I just have a question. So,
go for it.
In a sentence, you can have the same character many times, right?
Mm-hmm.
So, in the for loop that we're doing, we are going each character and we are kind of putting true false for that.
Yep, exactly.
So, like, isn't that like kind of like waste of time? Because if there are two C's, won't the true false array be the same for both?
No, because it's based on the position. That's a great question. So we've got, okay, so if we index in, so let's go ahead and take a look at this. That is a great question. Because you have, okay, so you have 297,291 sequences, right? In those, you have 40 different positions, right? And for each position, you're encoding, you have one value that's true, and the rest of them are false. So if you have a C at, position 20, and then you have a C at position 40, they're different because you're going to have 20 and then the other one's going to be 40, right? And so they're still unique values because they're literally in different places in our data. Does that make sense?
Okay.
Okay, cool. Which of course you would want, because you don't want to overwrite. You want there to be multiple values, right? And you want order. You don't want to collapse them in a way that you lose the order, right? So this says we have 40 values, and each character represents one of those values. And we have 121 different possibilities for that. And we have 300,000 chunks or sequences that we're pulling. Okay, let's build the model. And if you guys have any other questions, go ahead and please speak up. Okay. Okay, so let's go ahead and instantiate our model. We're going to use a sequential model. 128. And by the way, 128 is just kind of an arbitrary number. It's one of those things that you can input shape is going to be max length, comma, the length of characters. Sure, I've got the right number of parentheses there. Okay, we're going to add a dense layer. We're going to be, we're going to use softmax as our activation function. Include an optimizer. Loss equals categorical entropy, cross entropy. And we want our optimizer to equal optimizer. Okay. This is going to take a minute to run. Oh, that was actually fairly quick. Okay, you guys have seen the syntax before. I I don't want to spend too much time on it, except for the added thing here is we have our LSTM layer. This is actually the part that is doing that recursion piece that we talked about. So there's only one recursive level here. You can have multiple LSTM like levels. For sake of not making my SageMaker explode, I'm trying to keep it simple here. But as you can imagine, this is not going to be a highly performing model because I'm trying to keep it very simple. That's for you guys to play with tomorrow. As we talked about during the quiz, we're trying to predict. We basically got a multi-class prediction at the end. That's our outcome, right? We've got a single character that we're trying to predict, and it can be one of 121 different values, right? That's why on our final layer here, our final dense layer, we've got an activation function that is softmax. And then the rest of this you guys have pretty much seen. And optimizer, this is just, and I'll be completely transparent here. This is just an optimizer that is used in a lot of these sequential character in, prediction examples. And so I just inherited that. I honestly don't have anything special to say about this optimizer, except for that it's really popular in these examples. So, okay. I want to take a minute. I've given you guys some helper functions. We don't necessarily need to go through these in great detail. What I'm going to do real quick, I will go through the code in a second. What I want to do is I actually want to get this other code running because this one's going to take a lot. Okay, so at the end of the day, we've got 2 helper functions we'll review in a second. But to wrap up our final, like, putting together the model, the final piece of the model, we're going to just run a fit function. We've got our X and Y. We're going to include a particular batch size. We're going to include a certain number of epochs, and I'm actually going to change it to 2 because I don't want to be here all night. And what this is going to do is this is actually going to print out the, it's going to print out the seed, and then it's going to print out the predictions based on that. Okay, so let's go ahead and run that. And see, this is going to take a while. So while that is running, let's go ahead and go back and look at some of the helper functions that we put together. Okay. So okay, I think this one's more important with the time we have left. What we're doing in this helper function is to basically take each epoch of the Keras model and take that state and ingest it as an argument. And what we're going to do is we're going to pull a random seed from that index. And then what we're going to do is we're actually going to generate, we're going to use our model to make some predictions, and effectively it's just going to spit out, we're doing this very quickly. We're printing out, we've got 400 different characters that we're going to fill. And we're basically going to, based on the model that we have trained, we're going to, for each epoch, make a prediction based on a random seed. Okay, so obviously we don't want to make a prediction based on all 300,000 chunks, right? And so what it's going to do is it's going to randomly pull some data out of there and say, okay, based on this, here's what our model is actually printing out, or this is what we're actually predicting. What are the subsequent characters? And what we're going to do is we're going to go from 40, which is our seed, right? Our random seed sequence. And we're going to print out up to 400 characters. And let's see how good it is. Okay, so that in a nutshell is what's going on here. And so you can actually see how this model is behaving. And so there's a reason we want to do this, because in the first example we had, there wasn't a lot of transparency into what was going on. The model was saying, oh yeah, I'm 80% accurate. I'm 80% accurate. Well, until you look at the text, you don't necessarily know how useful it is. And so what we're getting here is we have our seed on the south lawn of the White House, right, is what we would predict. We would predict the next value to be an E, right? And it's actually not producing a lot of useful data. Let's walk through, and so remember, we're still early on in this as well, so we've only got 2 epochs that we're walking through. Let's give it a minute to actually pull out a couple more predictions that we can look at. It would take half an hour to run the final thing, and it does get better when you run it with 5 or more epochs, but it just does go to show that early training or early rounds of training have a lot of adjustments, have a lot of error in them, right? And I'm sure that illustrates that point pretty well. Okay, someone have a question. I hear someone unmuting, and I see you making a funny face, Martin.
Well, I was just trying to figure out. I thought we're predicting one character. Why is
we are? So we're predicting one character, but we can go farther out. Does that make sense?
Why do we want to go farther out?
Well, because one character is not as useful as predicting farther out. We're basically, here, let's go ahead and look back at the callback function itself. So you can, so let's say that we're predicting stock price, right? We can look at the previous month, right? And then we can try to predict the next day, is it going to go up or down? That'll actually be a pretty decent model, probably, right? If we're just basing our information on one day. It's a more interesting prediction to try to go farther out. And so what you're actually going to see is as this goes, it's going to get White House correct very quickly, actually, right? Or something resembling what we would expect it to be. However, and so the earlier stuff, so if we go to like character number 41, 42, 43, it's actually going to pull something that is readable. But as you go farther out, the prediction is not going to be as great. And that's kind of the point. That's why we want to go a little bit farther out. Does that make sense?
Yes. So we just want to see that the prediction gets weaker and weaker the further out we get. It doesn't, like, extending our prediction doesn't help.
No. It's just a proof of concept. No, not at all. In fact, there's actually benefits to, as you go farther out, and this is a universal concept, as you go farther out in your predictions, the predictions are not nearly as good because you're getting farther and farther away from sort of that source of truth. I mean, again, if we're looking at the last month, it'll be really good at predicting the next day, but it's not going to be great about predicting a week from today as strongly as you can predict that one day out. Does that make sense?
Yeah. Let me ask my question again. Predicting the 41st character, I thought that was our goal. By predicting more than that, does that help predict our 41st character better or worse?
Well, you're not changing. So nothing that comes downstream of that's being printed out is going to impact the 41st character.
Because that's how we're training. Yeah.
Right. We do, while this is running, and I'm sorry for jumping around, it's just a little tricky when we've got these things that take so many resources. Let's go back and actually walk through what's going on in this function, because I think this is important, okay? So effectively what we're doing is we're taking the epoch in as an argument, right? We're going to, I think the random seed piece makes sense. We're basically just pulling a random value, and we're going to use that as our starting point, right? It's random somewhere within our within our corpus. We're going to create an empty string to sort of start, and then it's going to be a generative function that, starting with the seed, prints out predictions as it moves farther out, right? So let's take a look at what that where the 400 characters come from. So we have, we're making our prediction, or we're initializing an array of zeros. Those are our X predicted values. And so what it's doing is it's actually going to be taking in, as it's generating predictions, it's going to be including that to make predictions on the next. So like, think of it this way. If we've got, it's training on increments of 40, right? It's going to be producing 41. It's going to then be including 41 as part of the prediction for 42. Does that make sense? Which is why the predictions get worse. Because if there's any error in that first one, so let's say it throws in like a white space where it shouldn't be, it's then going to use that to inform the next character that comes along, right? Okay, so anyway, we're basically including those values, and as we're building our list of characters, we're plugging that whole thing into our to making a prediction, right? Hopefully that makes sense. If you want me to phrase that another way, I'm happy to. Okay, and so after that, what we're doing is we're really just printing out the information. Okay, does that make sense? Okay, good. I'm getting some nods, getting some thumbs up, getting some people nodding off. Okay, I'm gonna go ahead and pause here and check in the chat. Okay.
I got a quick question, if you don't mind.
Yep. Yep, please do. What's up?
So this is just projecting basically the next character in a sequence of words. So for something like text prediction, like on our phones, would it be the same, but we're like tokenizing the words essentially? And that's how that works?
Exactly. And actually, that is the entire point of your assignment for tomorrow, is for you guys to take what you learned in NLP, apply the code that I've given you, and I want you guys to do something more useful than my model, which prints out kind of gibberish, right? And so what you're going to do is you're actually going to ingest the text from a Shakespearean, play or sonnet, and you want it to do some stuff with that, right? So I would recommend you use words as opposed to characters, because as you can see, printing characters out one at a time is not particularly useful. It's kind of a miracle this thing actually printed out anything legible. I would also encourage you guys to use more than one. Use your credits. Use your Amazon credits, which I don't have, and use multiple layers. You guys know how to tweak hyperparameters at this point. You can use a different number of, obviously you're going to use more epics. You want to use more epics. I promise you want to use more epics than 2. Really, let's see if we can actually kind of improve this a little bit. Let me go ahead and run it on 5. It may be done by the time class is done. But use more epics. I want you guys to do things like change your batch size. Dive into the LSTM layer documentation, try to figure out if there are any other models that you could, or any other hyperparameters that you might want to tweak. Unfortunately, we're just getting into the universe where these things take forever to run. Okay, So that actually gets us to the end of class, and I'm really glad we were able to get through everything. So before we enter the Q&A, what I just want to review real quick, what have we done today? And I will share this code as soon as this thing's done running. We've effectively built from end to end a recurrent neural network that makes predictions based on text. What we spent a lot of time doing was cleaning the data, putting it into effectively a multidimensional one-hot encoded array, which we then fit in, and it made predictions based on. Okay. What questions do you guys have? None? Okay.
I had a question.
Go ahead.
So I thought through this exercise we'd be able to, I mean, obviously the 41st character is most dependent on the few characters behind it.
Yep.
Is there a way to check the weights of those characters as a predictive model or something like this for, I mean, we're feeding it to a neural net, so I don't know.
Well,
I thought that was the whole idea of discussing this in context of the long-term, short-term
memory unit, yeah.
Yeah.
Well, what I did say at the beginning of class is that we're not going to be able to, for these things, this is a high-level overview. The goal is not to dive in to understand how the weights are being updated, because as soon as we get into the recursion, it gets outside the scope of our learning objectives.
Okay. I mean, I have no idea. I feel like I have no idea how the recursion algorithm works at all. And
do you want to step back and review that piece again?
Sure. Yeah.
No, I'm happy to. It was also 2 hours ago, so.
Yeah. I don't know. I feel like I'm at kind of a loss to develop an intuition of how this neural net does a good job with NLP exercise that we're doing. I don't.
Okay. Hold that thought. I will review. I want to make sure you guys get the code. I'm just uploading the notebook real quick. So again, and I can understand why this is a little bit difficult. The goal is not to do a deep dive on these things. I want you to understand at a conversational level how and why recurrent neural networks are good for particular tasks. And what I'm hearing you say, correct me if I'm wrong, is that you're not walking away with that understanding as to like, why is this particularly good for, in this case, text-based prediction? Is that correct?
Yeah, among other things. I mean that's the main issue for at least this discussion.
Okay, totally. Let's go back and revisit. Let me.
Yeah, and I mean, you said. Okay.
No, I'm listening. I'm also uploading the notebook.
Yeah, I mean, I know you said we're not doing a deep dive on how the weights are being updated, but it'd be nice to even see the final weights just to demonstrate that, I assume that the early characters will have this vanishing gradient problem, and just demonstrate that the I don't know, some sense of the final results of our neural net training?
I kind of need to reiterate what I said at the beginning when I first started talking to you guys, was that the transparency doesn't really exist in a way that's easy to explain. Remember the multi-layer perceptron? It took us 2 hours to like walk through and thoroughly discuss every single step, including backpropagation and gradient descent. That was a learning exercise we did on a really, really simple model. It's not something we're able to do for this type of model. Like, our goal here is to teach you application, not
theory. Yeah.
Right. Not the deep dive that you're looking for. And unfortunately, this just isn't, I don't have the time. It's not in the curriculum. It's out of scope for what we're trying to teach you. So what I can do is I can try to find some additional resources for you that would help you better understand the intuition. And I would welcome a deeper conversation during office hours, which we always have. Right?
Yeah, thanks, sorry.
Okay, no worries. Okay. Okay, hold on a second. Okay, does anyone else have any questions? Like, for instance, what is the vanishing gradient problem? That's an important one. What is an exploding gradient? That is an important concept that you guys need to know. So I've got the node diagram back up, and I'm happy to walk through this again if you still think that would be useful. Do you still want to review this, Martin?
Yeah, if we could.
Okay, yep, absolutely. Okay, so remember, these are still based upon feed-forward networks, right? And what are we doing in feed-forward networks? We're taking the weighted sum, we're calculating the gradient, we're basically trying to review, we're trying to make updates to the weights that move us towards minimizing our error, right? That's still, we're still building on that, okay? What we're doing, and what we described in the previous unit, was a simple additive model, right? Where we went back through and we basically added things together. And it could be positive or negative. Now that we're adding in the recursion level, this increases the dimensionality of the number of updates to those weights exponentially, right? And so for every iteration that you go through, again, we want to think about this as a loop, right? So our loop is sort of represented by our by the arrow here. You potentially have, again, it's an exponential change, right? And it can be exponentially increasing or exponentially decreasing.
Keri,
and so,
I'm sorry to interrupt. I think we're not seeing the screen that you're sharing. It's still showing your list of Jupyter notebooks. It's not showing the diagram or anything.
Sorry, rolling up. Here we go. This is what we're looking at.
There we go.
Yep, thank you. So logic, same things I said still apply. So instead of it being a simple additive update of weights, this takes on this becomes exponentially, it can increase more quickly or decrease more quickly. And what that means is that if you have, if you have something that would be at the random initialization of your weights or whatever else it is, it can make your gradients explode. In other words, they get really, really big, way too fast. Or there's the vanishing gradient, in which case they sort of disappear, right? And effectively your updates to your weights are, if you're increasing by an infinitely small amount, you're effectively not increasing those values, right? So that is the vanishing gradient and the exploding gradient. Those are problems that come with traditional neural networks, right? And I think, Martin, maybe the piece that didn't quite make sense was the fact that when you start talking about the long short-term memory, you've got this concept of gating, okay? And so as part of that recursion, what an LSTM unit does is it actually applies what are called forgetting gates and remembering gates. And what it will do is it will actually add one more loop inside here, and it will make it an explicit step to either increase a weight or decrease a weight based on whether or not they want to amplify a signal for a given neuron or decrease that signal, right? So if that neuron, let's say there's a hidden layer and our first neuron is not providing anything useful, right? Forgetting gate will sort of like help modulate what's coming out of that. The other thing that's important to recognize is that by applying our activation functions, this also helps, as we've discussed before, limit the signal that comes out of those neurons. And so that also helps correct the, vanishing or exploding gradient issues, because you're reducing the range of possible values for those updates. Okay, so that's a really high level. There are a lot of different ways to organize these different elements, right? But at a very, very high level, does that make sense, Martin?
Yeah, I think so, yeah.
Okay, cool. Okay, so this recursive element. So there's two issues with recursion. Recursion is what makes it work for sequences, right? I can try to rephrase that if that doesn't make sense, but it's the fact that it's a recurrent network that makes it useful for dealing with sequences, because it can handle repetition more gracefully. It can handle, it's basically it's the looping element of it that makes it amenable to solving those types of problems. The LSTM piece of it, so the gating piece of it, that's the part that corrects for the vanishing gradient and the exploding gradient issues. So LSTM is a modification of recurrent neural networks. And the reason they're so popular is that they're just more robust against those particular types of issues. Okay, I see a lot of people have dropped them. So it's late. Let's put a pin in it, okay? Let's have office hours at 7 o'clock tomorrow, and I'll do as deep a dive on this as you want, Martin.
Okay.
Okay.
So, sorry if I was being rude. I don't know. I just did not ask.
No, I think you were pressing the boundaries exactly as I expected you would, and that's and I needed to say it, that I will teach you as much as I can, but in a 2-hour lecture, I need to make sure the basic questions are answered before I need to make sure people understand what I just talked about before we do any kind of deep dive on the more advanced materials or the math. And candidly, this is not, this sprint is not where we learn. That's not where we take that deep dive. This is a survey. It's a survey sprint. I wish they have whole graduate, you can get a PhD in this stuff and not fully understand it. And we're trying to condense it into like 3 lectures. Okay. are there any other questions for those of you guys who are still around, like on the basic stuff, on the example we walked through? This is very abstract, guys, and I can understand why it's difficult to grapple with that.
I dropped a couple helpful articles in the channel if anyone wants to take the time to read those, just on exploding and vanishing gradients. They're really short.
Cool. Thank you, Annika. Okay. If there are no other questions, I'm going to go to bed. Martin, let's talk tomorrow. That feels fair.
Yeah. Thanks.
Yeah. Okay. I'm going to, and I know I need to hit okay on the upload so that you guys can actually see the notebook. It will be in the channel in like 1 minute. Okay. Have a nice night, guys. We'll talk to you tomorrow, office hours at 7 Pacific. Good night.